Describe the periodic table as an arrangement of elements in periods and groups and in order of increasing proton number, atomic number. Describe the changes from metallic to non-metallic character across a period. State that group 8 noble gases have full outer shell. State that the number of outer shell electrons is equal to the group number in group 1 to 7. State that number of occupied electron shells is equal to the period number. Describe the periodic table as an arrangement of elements in periods and groups and in order of increasing proton number, atomic number. Periodic table is the arrangement of elements in the order of increasing proton number. These are the proton number for elements. You see 3, 4, 5, 6, 7, 8, 9, 10, and so on. Proton number and atomic numbers have same meaning, that is the number of protons present in the nucleus of an atom. We also know that we can predict the number of electrons by knowing the proton number. The elements are placed in different groups or families. It is on the basis of their physical and chemical properties. These are different families. Family number 1, group 1, 2, 3, 4, 5, 6, 7, 8. It is on the basis of their physical and chemical properties. When we say physical properties, it means state at room temperature, pressure. Physical properties mean state at room temperature, pressure, boiling point, melting point, color, density, etc. And the chemical properties mean the way elements react to form new substances like elements and or compounds. Periodic table can be used to predict the properties of the elements. There are so many elements, therefore it becomes mandatory to classify them. Describe the change from metallic to non-metallic character across a period. Metals are present on extreme left side of the periodic table. You see, these are the metals. They contain 1, 2, 3 valence electrons. The group number is telling us the valence electrons. Non-metals are present on right side of the periodic table. These are non-metals. They contain 4 to 7 valence electrons. It means that if we move from left to right within the same period, the character of elements change from metallic to non-metallic. So metallic to non-metallic. Staircase line divides metals and non-metals. This is staircase line. Underneath this staircase line are metals. These all are metals. Above staircase line, there are non-metals. These are non-metals. On or close to staircase line are metalloids. Metalloids are intermediate of metals and non-metals, that is between metals and non-metals, which means these are metalloids. These are metalloids. We can also say that if the elements are above the staircase line, it's a poor non-metal, and if below the staircase line, it's a poor metal. Poor non-metals means that it may show some properties of metals like silicon at high temperature is good conductor of heat and electricity. Si at high temperature is good conductor of heat and electricity. In the same way, this concept is applicable to aluminium. Aluminium is below the staircase line, which means it can act as a poor metal. It will show all the basic characteristics of metals like aluminium exist in solid state at room temperature and pressure, good conductor of heat and electricity, etc. But its oxide is amphoteric rather than basic. Aluminium oxide is amphoteric. Amphoteric oxides are between metal and non-metal oxide. They just act like both metal and non-metal oxides. State that the group 8 noble gases have a full outermost shell. This is group 8. Helium, neon, argon, krypton, xenon, and radon. They are also called inert or noble gases. Group 8 also known as noble or inert gases. They are unreactive because they have full outermost or valence shell. They have full valence shell. We can also say that they have stable electronic configuration. This tells that noble gases are unreactive or does not form any ionic or covalent bonds with other elements.
Welcome to Chain of Qualified Tutors. Unlock your academic potential with expert tutoring, from secondary school to graduation level. Master math, science, English, and more with personalized one-on-one guidance. Call or WhatsApp for a free demo session. We offer on-site and online tuition.
Inert gases does not react. State that the number of outer shell electrons is equal to the group number in groups 1 to 7. These are the group 3, 4, 5, 6, 7, 8. The vertical columns of elements are known as groups. Groups are vertical columns of elements. Group number tells us the valence electrons. And elements present within the same group have same number of valence electrons. This is a vertical column, group number 1, 2, 3, 4, 5, 6, 7, 8. We can predict the number of valence electrons for any group element by looking at the group number. For example, group number 1 elements, they have 1 valence electron. Group 2 elements have 2 valence electrons. Can you predict the number of valence electrons in group 4 and 7? It's very easy. By looking at the group number, for group 4, it should be 4. For group 7, it should be 7. Chemical properties depend on the number of valence electrons. Hence, the elements present in the same group have same chemical properties. Elements in same group have same chemical properties. State that the number of occupied electron shells is equal to the period number. Horizontal rows of elements in the periodic table is called periods. Periods are the horizontal rows of elements. These are the periods. So period number 1, period number 2, period number 3, 4, 5, 6, 7. Period number tells us the total number of occupied filled electron shells. There's a difference between having filled electron shells or complete shell. In order to understand this, we have to consider two elements in the same period. For example, period 2. Lithium is the first element. The proton number is 3, which means it has 3 electrons. Now distribute these electrons in different shells. We will get this Li 2, 1. You see the last electron, that's 1. It means it is not complete. It is filled, the last shell is filled, but it's not complete. Now the last element in this period is neon. The proton number of neon is 10, which means electronic configuration would be like this, 2, 8. You see, both the shells are complete. Therefore, we have concluded that elements present in the same period have same number of filled electron.
Describe the relationship between group number and the charge of the ions formed from elements in that group. Explain similarities in the chemical properties of elements in the same group of the periodic table in terms of their electronic configuration. Explain how the position of an element in the periodic table can be used to predict its properties. Identify trends in groups, given information about the elements. So here's the periodic table. So first of all, we'll talk about the relationship between group number and the charge of the ions formed from elements in that group. So if you look at this periodic table, you can see these numbers. These numbers indicate the group number. These are the numbers. This tells us the group number. 1, 2, 3, 4, 5, 6, 7, 8. Now, excluding group number 8, all these group shows or carries a charge. How we are going to predict the charge of the ion form? Group number 1, 2, and 3 are metals. And we know that from group 3 and onwards, there is a staircase line. This is a staircase line that starts between boron and aluminium. It will go like this. This is staircase line. What does this staircase line indicate? Below the staircase line, we have metals. And above the staircase line, there are non-metals. So for the metals, the charge on the ion will be equal to the number of electrons metal is going to lose during bonding. We know the group number for metals. This indicates the number of valence electrons. For example, group number 1, there are 1 valence electron. Group 2, 2 valence electron. Group 3, 3 valence electrons. So these are the number of electrons present in the valence shell of metals. And the metals, they are going to lose the same number of electrons during their bonding. So this will be equal to the charges on the metal ion. So as the metal atoms are losing electrons, so it will acquire positive charge. So group number 1, they will form positive 1. Group 2 will acquire positive 2. Group 3 will acquire positive 3 charge. These will be the charges on the ions formed by these groups. What about non-metals? From group 4 till 7, we have non-metals. In group 4, we have talked to non-metals, then there are metals down the group. So it's like a mixture of metal and non-metals. For non-metals, charge on the ion will be equal to the number of electrons an atom is going to gain during bonding. So how are you going to predict the number of electrons these non-metals are going to gain during bonding? It's very simple. What you have to do, you have to subtract the 8 from their group numbers. The group numbers indicate the number of valence electrons. So for group 5, if you want to work out the charge in group 5, what you will do, you will subtract 5 from 8. Why 8? Because 8 indicates a complete configuration of an atom, which is second shell and onwards. So we will write 8 minus 5, and you will get, sorry, there's a correction here. You need to minus the 8 from group number. 5 minus 8. The answer will be minus 3. So minus 3 will be the charge on group 5. Minus 3. For group 6, six minus 8, minus 2. For group 6, 6 minus 8 gives minus 2. Minus 2. Can you predict the charge of the ion formed by the group 7? Group 4 will write plus minus 4. Explain similarities in the chemical properties of elements in the same group of the periodic table in terms of their electronic configuration. The group number indicates the valence electrons. The group number indicates the same electronic configuration in the valence shell. For example, group 1 contains 1 valence electrons. Group 1, 1 valence electrons. Group 2, 2 valence electrons. Group 3, 3 valence electrons. Group 4, 4 valence electrons. Group 5, 5 valence electrons. So all the group members, meaning that elements present in the same group, have same number of valence electrons. Same valence electron or electrons mean same chemical properties. So the elements present in the same group behaves in a similar manner in chemical properties because of the same number of electrons in the valence electrons. For example, group number 1, they all are highly reactive metals. They will show same chemical behavior. When we are reacting group number 1 with oxygen, they all form oxide with the formula M2O. Why? Because the group number is 1. So the valency of the group number 1 metal will be +1. Oxygen belongs to group 6. As I have just discussed, the valency of group 6 will be -2. So the charge on on oxygen will be -2. Ignore their charges. So these will be subscripts now. The numbers will be subscripts. And in predicting their formula, these subscripts will be exchanged. So in the end, we'll get M2O. So the formula of the oxide formed by the group 1 metal will be M2O. They all will form oxide with the formula M2O. In the same way, you can predict the molecular formula or chemical behavior of other elements in the periodic table. Explain how the position of an element in the periodic table can be used to predict its property. You can also predict the properties of the elements in the same group if they are present in the same group. Although there is a trend. For example, if I will talk about group 1, there is a trend for group 1 metals. Group 1 metals. They have some unusual properties like soft. They are soft. They are soft metals. Metals are usually hard, but they are soft metals. Low boiling point, low boiling and melting point. They have low density. So these will be the common properties shown by all the metals present in the group 1. Although there is a variation in the values for the melting point, boiling point, and density, they are also highly reactive metals. They are highly reactive metals. That is, when they are exposed to air, they will react with everything: oxygen, water, producing oxides, hydroxides, etc. In the same way, you can predict the properties of other elements if they are present in the same group. Now here is a past paper question. Chromium is a transition element. Sodium is an element in group 1 of the periodic table. Explain how both chromium and sodium conduct electricity. Let's see the position of sodium and chromium in the periodic table. Sodium is present in group 1, which means it's a metal. And where is chromium? Chromium is in the middle of the periodic table, which means it's also below staircase line. So both of these are metals. So now you can answer easily for this question. As both of these are metals, so both of these conduct electricity due to the presence of delocalized electron. Due to delocalized electrons. Delocalized means mobile, free. They have free electrons which can move around. It helps in the conduction of electricity or current. Here's another past paper question. Group 2 elements show the same trends as group 1 elements. Which statement about elements in group 2 is correct? First of all, I am writing the trend for group 1 because then this will help you in answering these questions. So the trends in group 1, these are the trend in group 1. Trends in group 1. And remember, it's down the group. Melting point decreases. Density increases. Reactivity increases. Can say softness increases or hardness decreases. Hardness decreases. So I am going to read all the statements one by one. Then we will decide which of these statements are correct. The melting point of barium is higher than the melting point of calcium. Let's look at the position of barium and calcium. So here's the barium and here's the calcium. So melting point of barium should be lower than calcium. So this statement is wrong. Barium is more reactive than beryllium. Barium is below beryllium. Here's beryllium, and this barium. So barium is more reactive than beryllium. These statements look correct to me because in group 1, the reactivity increases down the group. So according to that trend, barium should be more reactive than beryllium. For your convenience, I am reading the other statements also. Strontium would not react with oxygen. Where's the strontium? Here's strontium. Strontium will definitely react with oxygen. As I've told you in group 1, they are highly reactive metals. They will react with everything. Like they react with oxygen and water, producing oxides and hydroxide. So strontium will definitely react with oxygen. This statement is incorrect. Magnesium is more dense than barium. What about the density in group 1? The density increases down the group. So comparing the position of barium and magnesium. Here's magnesium, here's barium. Barium is down than magnesium. So barium should have high density. So this is also incorrect statement. The only statement which is correct here is B. Identify trends in groups given information about the elements. You can identify the trends in groups when the information is provided. For example, there's another past paper question. Some properties of the group 5 elements are shown. So we have element, electrical conductivity of solid, melting point in centigrade, boiling point in centigrade. Use the information in the table. Predict the physical state of nitrogen at minus 200 degrees centigrade. Explain your answer. So physical state of nitrogen at minus 200 degrees centigrade. The melting point of nitrogen is minus 210 and boiling point is minus 196. It should exist in the liquid state. So answer will be liquid. Now you have to explain. So you can write minus 200 degrees centigrade is between the boiling and melting points. Here's another part of this question. Predict the melting point of arsenic. How you're going to predict the melting point of arsenic? If you look at the melting points of nitrogen and phosphorus, what is the difference? The melting point of nitrogen is minus 210 and phosphorus it's 44. So what I will do, I will add up these two and see the difference between these two. Difference these two will be plus 210, 44. What will I get? I will get 254. 254. So in this way, you can predict the melting point of arsenic. You can write 254 degrees centigrade by looking at the difference between the two. You can add up. You can add up this number to 244 plus 44 degrees centigrade. What you will get? You will get 298 degree centigrade. So what the marking key says that it should be between 500 degrees centigrade to 600 degrees centigrade. So according to the marking key, our answer is correct. Use the information in the table to explain how the structure and bonding in nitrogen differ from the structure and bonding in bismuth. Now, if you look at the melting point of bismuth and nitrogen, there's a big difference. The melting point and boiling point both are higher. Nitrogen is a non-metal, bismuth is a metal. If you look at the position of bismuth, where is this bismuth? I'm showing the staircase line also for your convenience. You see the group 5, here's bismuth and it's nitrogen. Bismuth should be a metal and nitrogen is a non-metal. So it's like a difference between, writing difference between metal and non-metal. And if you look at this table, you can easily predict the difference between it. Nitrogen is simple. Nitrogen is a simple molecule. So you will write nitrogen is a simple molecule. What about bismuth? You can say bismuth has a metallic structure. What else they are asking? They are asking about bonding. So in case of nitrogen, nitrogen contains covalent bond, while bismuth contains metallic bond. Describe the group 1 alkali metals, lithium, sodium, and potassium as relatively soft metals with general trends down the group limited to decreasing melting point, increasing density, increasing reactivity. Predict the properties of other elements in group 1 given information about the elements. Describe the transition elements as metals that have high densities, have high melting points, have variable oxidation numbers, form colored compounds, often act as catalysts, as elements, and in compounds. So here's the periodic table. So on the left hand side of the periodic table, You see the group 1. These are the alkali metals. We have lithium, sodium, potassium, rubidium, cesium, and francium. These all are alkali metals as they are in group 1. So they have 1 valence electrons. 1 valence electron. Remember, group number tells us the number of electrons present in the valence shell. So here's the snaps for 2 metals from this group. On the left side, you see these are soft metals. This is of lithium. And on the right hand side, it's the cesium. Cesium melts on our palm because the melting point of cesium is lower than 30 degrees centigrade or around 30 degrees centigrade. So let's continue talking about these alkali metals. Alkali metals are on the extreme left side of the periodic table. They're shiny when freshly cut. They form cations of formula M+, which means they lose 1 electrons. They lose 1 electron to form positive ion or cation. The formula will be M+. M will be any metal from group 1. For example, it can be Li+, Na+, K+. What is common in these? They all are losing 1 electrons. So question number 1, what makes alkali metals different from other metals in the periodic table? Although these are metals, but they have some properties which make them different from other metals in the periodic table. If you can recall, metals are usually hard, but they are not hard. They are soft, very soft. Metals have high density, but they have low density. Metals have high melting point and boiling points, but these have low melting points. And the important point, the last one, they are very reactive metals. They react with everything. React with everything like oxygen, O2, H2O in air. They react with both oxygen and water in air. That's why they are kept in kerosene oil. They are kept in kerosene oil so that they will not react. Okay, here's the question. Why reactivity in alkali metals increases as we go down the group? So let's come back to this periodic table. If you look at this periodic table, and if we talk about the trend in alkali metals, as you go down the group from lithium, sodium, potassium, rubidium, cesium, and francium, the reactivity increases. Reactivity increases. So down the group, the reactivity increases. But why is this? Let's consider two elements from this group 1. I'm taking example of lithium. The proton number of lithium is 3, which means it has 3 protons and 3 electrons. So this will be the nucleus of lithium. We have proton and neutron. We have 3 electrons. So in the first shell, there will be 2 electrons, 1, 2. And the second shell, it will be 1 electron. Now after lithium, we have sodium. The proton number of sodium is 11, which means it has 11 protons and 11 electrons. This will be the nucleus of sodium, neutron and proton. First shell, there will be 2 electrons, 1, 2. Second shell, there must be 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. Now 1 electron is left. In the third shell, we have 1 electron. What about potassium? The proton number of potassium is 19, which means it got 19 protons and 19 electrons. For potassium, I have to make 3 shells. First, I have nucleus, neutron and proton. This is the first shell, second shell, and third shell. Now I'm going to place all the electrons. In the first shell, there are 2 electrons, 1, 2. In the second shell, 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 2, 10. 18 minus 10, and 19 minus 10, 9 electrons are still left. So in the third shell, there will be 8 more electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now 1 electron is left, which will come in the fourth shell. You see the size, the atoms become larger and electron shells increase. See the increase in electron shells and atoms become larger. So the attractive force of nuclei for valence electrons decreases. So as you go down the group, in this group, the attraction for the valence electron decreases. Attraction of nuclei for valence electron will decrease, which means it becomes easier for a metal atom to lose its valence electrons. It becomes easier to lose valence electron. That's why the reactivity increases down the group. In fact, down the group, we have highly reactive metals in the periodic table, like cesium. It reacts explosively. Both rubidium and cesium, both of these are highly reactive metals. So let's talk about some reactions of alkali metals along with observations. We have a reaction with air or oxygen, then we have reaction with cold water and with chlorine. For lithium, it burns with red flame on reaction with oxygen and produces white solid. And when lithium is reacted with cold water, it floats on water, then it reacts quickly, bubbles of gas will be produced. With chlorine, it burns with bright flame and white solid will be formed. What about sodium? Sodium with air or oxygen burns with bright yellow flame and white solid is produced. With cold water, it also floats on water but reacts fast as compared to lithium. The smoke will be produced here. We will not get any bubbles, we'll get smoke. Instead, we'll get smoke. What about chlorine? When it will react with chlorine, it burns with bright flame just like lithium. Again, white solid is produced. What about potassium? Potassium now burns violently with lilac colored flame and white solid is produced on reaction with oxygen. With cold water, it reacts violently. So just like lithium and sodium, it also floats on water, but it reacts violently. You see the things are getting quicker and faster. There will be violent reaction. Sparks will be produced. And with chlorine, it burns vigorously. With chlorine, a white solid will be produced. Now for the rubidium and cesium, you can easily predict the reaction. There will be explosive reaction. Explosive reaction. Or you can even write destroying the whole apparatus. In case of reaction with water, any gas produced will catches fire. Now here are some reactions of alkali metals. M represents any alkali metal, like you have lithium, sodium, potassium, rubidium, cesium, or francium. Now, if you want to react lithium with oxygen, the reaction will be 4Li plus O2 gives 2Li2O. How you will get the formula Li2O? This is lithium oxide. Recall the concept of valency. Lithium is in group 1, na? So the valency of group 1 will be +1. Oxygen is in group 6. The valency of group 6 is -2. Ignore the charges. 1, 2. Now these will be subscripts. Subscripts will be exchanged. So you'll get what? Li2O. In this way, you'll get the formula Li2O, lithium oxide. Now, when you react these metals with water, you'll get two products. You will get metal hydroxide and hydrogen gas. This is gas, hydrogen gas. So, if you are reacting sodium with water, what you will get? Na plus H2O. You will get metal hydroxide and hydrogen gas. What will be the formula of metal hydroxide? Sodium belongs to group 1. So again, the valency is +1. What about the charge on the hydroxide ion? Hydroxide ion, the formula of hydroxide ion is OH. It carries -1 charge. Ignore the charges. Now these subscripts will be exchanged. So it's very simple. You will get NaOH. Sodium hydroxide. Now I will balance the equation. So I will write 2 here, 2 here, we have 2 here. Now it's balanced. The last reaction is with halogen. What is X? X can be any of these halogens. Halogens are group 7 elements. Fluorine, chlorine, bromine, iodine, or astatine. Now if you react potassium with chlorine, what you will get? K plus Cl. You can't write Cl. Halogens, they all exist in diatomic state. So you have to write Cl2, not Cl only. What will be the formula of the compound formed between K and Cl? K belongs to group 1, the valency will be +1. Cl belongs to group 7, the valency will be -1. So ignore the charges. Subscripts will be exchanged 1, 1. So in the end, you will get KCl. This is potassium chloride. Now let's balance the equation. Write 2 here, 2 here. Now it's balanced. In the same way, you can predict the reactions of other alkali metals with oxygen, water, and halogens. Now let's talk about the trends down the group. So there's a decrease in melting point. There's also decrease in boiling point. What is ORA? ORA is or reverse argument. You can write the reverse argument. When you say reverse argument, so it means we'll go up the group. So up the group, what's happening? Increase in melting point. Increase in melting point if we move up the group. Now the other trends, there's an increase in density down the group. There's increase in reactivity down the group. There's decrease in hardness. You can say there's increase in softness down the group. So you can write there is increase in softness. Again, you can have any reverse argument like ORA or reverse argument. Now here's past paper question. Chemical properties of some group 1 elements are shown in the table. So here we are having element, reaction with cold water, then we have reaction with oxygen, flame test color. Number 1, add to the table the flame test colors for sodium and potassium. It's very easy. For sodium, you get yellow color. For potassium, you will get lilac. Lilac is purplish. The predicted reactions of rubidium with water and with oxygen. So you can write explosive reaction, as I have already mentioned, explosive reaction. So it will also form a colorless solution. The statement will be same, forms a colorless solution. With oxygen, it again you can write explosive reaction, and it will also form oxide layer. Name the gas produced when group 1 elements react with water. I have already discussed. It is hydrogen gas. So you write hydrogen here. Now let's talk about transition metals. Transition metals. Here in the middle, they are between group 2 and group 3. This is group 3 and group 2. So these all are transition metals. You have notable elements of transition metals like copper, zinc, iron. These are very common. Gold, silver, these are also common. And other transition metal which is used in thermometer, it is mercury. The symbol of mercury is Hg. Here it is mercury. So here are two transition metals. This one is copper. These are copper. You know, copper is used in the wiring. And this is rusted iron. It's actually rusted iron. It's not pure iron, rusted iron. It's rusted iron ladder. Okay, now transition metals, they possess all key characteristics, that properties of metal, which means they are hard, high melting point, melting or boiling point, high density, malleable and ductile. You know, the malleable can be changed to different shape, and ductile, good conductor of heat and electricity. Good conductor of heat and electricity. Good conductor of both heat and electricity. Now, what makes them different from other metals in the periodic table? They have variable oxidation states or numbers or valencies, except zinc 2+. So variable valency means they have more than one charge. Like copper, it can have +1 and +2. Iron, it has +2 and +3. They often form colored compounds. Cu2+ is blue in color, Fe2+ green in color, Fe3+ reddish brown, etc. There are other colors for the other transition metals. We don't have any details. We are limited to copper 2+, Fe2+, and Fe3+. So transition metals or their compounds can act as a catalyst. What are catalysts? Catalyst increases the rate of reaction. And you know that how they do this, they decreases the activation energy, or they provide the alternative route to the. Here are some compounds of transition metals. For example, you have compound of chromium. This is chromium compound. Potassium dichromate, it's an iron compound. It is iron 2 sulfate. It's cobalt compound. Symbol of cobalt is CO. Cobalt 2 chloride. It's copper 2 sulfate, blue in color. It's a copper compound. You have nickel compound, nickel 2 sulfate. You see, in all of these, except the first one, they have shown the charges on transition metals. The reason is that they have variable valency. That's why it's very important to show the charges or valencies. So here we are having some uses of these transition metals, which is in your syllabus. For example, V2O5. It's a compound of vanadium. It's vanadium pentaoxide. It's used as a catalyst in contact process. Contact process is used for preparing sulfuric acid. And during the preparation of sulfuric acid, there's a step in which there's a conversion of SO2 into SO3 taking place. It takes place in the presence of catalyst V2O5. There's another process to make ammonia. It's known as Haber process. And in Haber process, iron is used as a catalyst. So in manufacturing of margarine, we use nickel. And when you are interested in manufacturing O2 from H2O2, H2O2 is hydrogen peroxide, we use manganese dioxide or Mn4 oxide, MnO2 is the formula. So here are more applications of these transient metals. There are some different things used, like for examples, a screwdriver. This is screwdriver. This is screwdriver. These are keys. This is a scale or saw kind scale. This is a nut opener, tire nut opener. Here are some wires. So transient metals are also used in this. So we have past paper questions. Describe two differences in the physical properties of chromium and sodium. Looking at the position of chromium and sodium, chromium is a transition metal. So you can write any of these differences between these two. We have chromium, sodium. You can write chromium. It is hard, form colored compound. Variable valency. Used as catalyst. These are differences. So for hard, you can write here for sodium. It's soft. It's not colored. It's not colored. It does not form colored compound. It has fixed valency. That is one. You can also write other points like chromium have high melting point, high density. Sodium got low density, low melting point, etc. Here's another question. Potassium reacts with water to form a gas which pops up with a lighted splint. Complete the equation for this reaction. There's a reaction. It's potassium plus H2O gives 2 KOH plus gas produced in this reaction is H2. This is a gas which pops up with a lighted splint. Now let's balance this equation. I will write 2 here. Now this equation is balanced. If you count the number of atoms, potassium, 2 on the reactant side, 2 on the product side. What about hydrogen? 2 to the 4, 4 on the reactant side, 2 plus 2, 4 on the product side. What about oxygen? Oxygen is 2 on the reactant side and 2 on the product side. It's bad physical properties of chromium and sodium. Let's look at the position of chromium and sodium from the periodic table. Chromium is among the transition metals and sodium belongs to group 1 metals. Now you can easily write down the differences between these two metals. And they are talking about the physical properties of chromium and sodium. Whatever you write for chromium, the reverse statement for sodium will be true. For instance, if you write for chromium, chromium is hard. You can write high density, high melting point, has variable oxidation state or number. Compounds of chromium are colored. Now for sodium, we have any reverse statement. For example, I've written chromium is hard. You can write sodium is soft. In the same way, you can write the opposite statements for sodium, like chromium has high density, you write sodium as low density. low melting point. Does not have variable oxidation number or oxidation states, or you can even write fixed oxidation number. Compounds are not colored. Now here's another question. Potassium reacts with water to form a gas, which pops with a lighted splint. Complete the equation for this reaction. Here's a reaction between potassium and water, and you know that it will always produce metal hydroxide, which is potassium hydroxide in this case, and the gas will be produced, and this gas pops up with the lighter splint. The formula of this gas is H2. Now let's balance the equation. We write 2 here. Now this equation is balanced. So here we have the learning outcomes of this video lesson. Describe the group 7 halogens, chlorine, bromine, and iodine as diatomic non-metals with general trends down the group, limited to increasing density, decreasing reactivity. State the appearance of the halogens at RTP as chlorine, a pale yellow-green gas, bromine, a red-brown liquid, iodine, a gray-black solid. Describe and explain the displacement reactions of halogens with other halide ions. Predict the properties of other elements in group 7, given information about the elements. Describe the group 8 noble gases as unreactive monatomic gases and explain this in terms of electronic configuration. So here's a periodic table. First of all, I'm going to show you the halogens. These are the halogens in the periodic table or group 7. Now halogens, what does the word halogen means? Means salt maker. Halo means salt, gen means maker. Salt makers. Because they all form salt when reacted with metals. These non-metals are found on the right side of the periodic table. You have seen this. They have 7 valence electrons. You see group 7. Group 7 means they have 7 valence electrons. They are very reactive non-metals. They are non-metals. They are not metals. They exist in diatomic states. For example, F2Cl2. You can predict the formula for the molecules of other members like bromine, Br2, iodine, I2. Even you can predict the formula for astatine, At2. They have low density. They have low melting and boiling points. They are non-conductor of heat and electricity, which means they do not have mobile or delocalized electron. Means their electrons are not free in the valence shell. They are non-malleable and non-ductile. Non-malleable means cannot be made into different shape. Non-ductile means cannot be made into wires. They gain 1 electron to form negative ion or anions. The other name for negative ion is anions. So what they will form? They will form negative ion, means they will acquire minus charge like this, X minus. X can be any one of these halogens: fluorine, chlorine, bromine, iodine, and even astatine. The trends. Let's talk about the trends in group 7 non-metals down the group. Now, melting point, boiling point, it increases down the group, which means that the state will change. Density also increases down the group. Reactivity decreases down the group. Why reactivity in halogens decreases as we go down the group? As we go down the group, electron shells increases. Distance between the nucleus and incoming electron in valence shell also increases, which means incoming electron experiences less attractive force by the nucleus. There will be less attractive force between the nucleus and the incoming electron because the distance between the nucleus and the valence shell increases down the group. Now, this is the appearance of halogens at RTP. What is RTP? RTP means room temperature and pressure. See, fluorine state exists in the gas state. The color will be light yellow. It's yellow, light yellow. For chlorine, it also exists in the gas state, but it's yellowish green or pale green gas. Bromine is a reddish brown or brown liquid. Iodine is a purple gray solid. Acetylene is black solid. Now, what about their color in solution? Now, color in the solution, the color become light. For instance, fluorine, the color of fluorine becomes colorless in the solution. For chlorine, it becomes light yellow. Bromine, orange. Iodine, dark brown. For acetylene, it's not applicable. You see, this is the color of these halogens. The first one is chlorine. Second one is bromine, liquid. And last one is iodine, solid. We have gas, liquid, and solid. Now, looking at their colors, you can easily say that, you can easily predict color darkens down the group. This is a trend for color. Color darkens down the group. Or you can write reverse argument. Reverse argument will be color become lighter up the group. So you move from down to up. So here's another important reaction in halogens, displacement reactions in halogen. What are displacement reactions? You should know the displacement reactions. First of all, the concept of displacement reactions. What are displacement reactions? Reactions in which highly reactive element displaces the less reactive from their compounds. These are the displacement reactions. Now, halogen present top of the group displaces halogens present below them from their respective compounds. This is because the halogens present at the top of the group are more reactive than halogens below them. Here, there is a halogen. These are the halogen. You see, fluorine is more reactive than all of these. Same way, chlorine is more reactive than bromine, iodine, and astatine. Chlorine is more reactive than bromine, iodine, astatine, but less reactive than fluorine. In the same way, you can predict the reactive behavior of bromine and iodine. What do you think? Iodine, about iodine, what do you think? Whether it will be more reactive than bromine or less reactive? Explain. Here's the reaction between chlorine and potassium iodide. The product will be KCl plus I2. Chlorine plus potassium iodide produces potassium chloride and I2. The reason is that chlorine, Cl2 or chlorine is more reactive than I2. You can even write chlorine is above iodine, I2. You have reverse argument for this also. For instance, for the first statement, you can write iodine less reactive than chlorine. Second statement, iodine is below chlorine. So here's the question. Aqueous chlorine reacts with aqueous potassium bromide, Cl2 plus 2 KBr gives Br2 plus 2 KCl. The product is Br2 and KCl. State the color of Br2 aqueous. Now they are asking about the color of bromine. You can write any of these colors. You are allowed to write orange. You can even write red brown. Explain using ideas about the reactivity of the halogens. Why aqueous bromine does not react with aqueous potassium chloride. I have already explained this reaction, the reaction between chlorine and potassium iodide. You can use these statements and apply this idea about reactivity of halogens in this question. Now let's talk about inert gases or group 8 elements. Group 8. Group 8, this is the group 8. Group 8, we have helium, neon, argon, krypton, xenon, and radon. These all are inert gases or group O or group 8 elements. These elements are present on extreme right side of the periodic table. They exist as monatomic gases, He, Ne, etc. Monatomic gases means if you have cylinder of helium, you have atoms of helium, not molecules. You have only atoms of helium. In the same way, you have other inert gases existing as monatomic gases. They are also known as noble gases. They are very unreactive gases. It does not combine either covalently or ionically. What is the reason? You can write any one of these. The best reason will be they have complete valence shell. Or you can even write they have stable arrangement of electrons. They have stable arrangement of electrons. This is the reason. Now, inert gases, the boiling point increases as we go down the group. This is a boiling point. So these are boiling points mentioned in Kelvin. For helium, it's 4. For neon, it's 20.18. For argon, it's 39.948. For krypton, it's 83.3. For xenon, it's 131.429. In radon, it's 222.1. You see the difference in the relative atomic masses? Helium 4, neon 220, argon 40, krypton 84, xenon 131. See, this will be the reason. As we go down the group, what is happening? Relative atomic mass increases. AR or relative atomic mass increases. So which means that attraction between the atoms also increases. Attraction between the atoms also increases. which means that they need high amount of energy to break it down. So here are some uses of inert gases. They are usually used in providing inert atmosphere. In providing inert atmosphere. Inert atmosphere means the element metal or non-metal will not react. Some of the uses for helium like weather balloons and airships, neon, advertising lights, argon gas for electric bulbs and welding and making steam, krypton, lasers and gas-filled electronic devices, xenon, electronic flash gun, radon, natural radioactive gas. So these are the inert gases or noble gases. Here's a question. State why noble gases are unreactive. I've already explained this. Number 4, which statement about the properties of the elements in group 8 of the periodic table, helium to xenon, is correct? Now I'm reading all these statements one by one. So we'll check which of these statement is correct. A, argon reacts with iron to form a compound. This is wrong because they do not react to form any compound. What about the statement number 2? B, helium is less dense than air. The density of air is around 33 grams per centimeter cube. For helium, it will be 4 grams per centimeter cube. So this looks correct to me. This statement looks correct to me because helium is less than air. For your convenience, I'm reading the other statements, other choices also. The elements change from gas to solid down the group. You see, in this group, they all exist in the gases, so we don't have any solid or liquid in this group. So this statement is wrong. Last choice, the elements exist as covalent molecules. This is also wrong because they do not react covalently or ionically. So choice B will be the